example, as a protections to prevent different kinds of failures, such as we have what is known as the Pucox relay, which is focused on the incidence fault for the transfer. For example, if we have overheating conditions. Then we can also use the ERP fault relay. So from the names, you can tell is being dealt with short circuit to ground phenomena. Overcurrent relay is same as what we have learned for chapter 4, dealing with overcurrent situation for a transfer. For example, we have a short circuit between the transverse winding, or we have overload conditions. And the last one here, we have differential protection scheme. So we have two kinds. One is not as differential relay. The other one is actually the improved versions of differential relay, not as biased differential relay. So these two will be introduced to you as well. And the last topics here will end this chapter by talking about what is the possible issue faced if we are implementing the differential protection scheme for the transformer. All right, so that we can ensure this scheme can look probably to deal with overcurrent situations. Okay, so now let's move on here. So the lesson learning outcome for these specific chapters, we have 3. First, you are able to tell the difference between the true fault and non-true fault phenomena for a transformer, so that whenever you are developing the protection scheme, it will not trip whenever it shouldn't, since that is a non-true fault situation for a transformer. It's a natural behavior for that transformer. And after this, you also understand the operations, the ideas behind different protection scheme we have for the transformer, so that for example, if you want to have the protection scheme that deals with overheating situations, so you know what is the right scheme to be applied. And the last one here will be able to discuss the problems faced by the differential protection scheme for the transformer. All right, so now let's move on here for the introduction. So what is actually a transformer is? I believe you know what is this. So now, if you refer to this diagram, right, you can see there are many transformers used in between as a vital link to transform up and down the voltage value of the direct electricity from the power plant in this power transmissions and distributions networks. So you can see, right, this transformer is actually very important component to be protected in the power system. So let's check out its definitions here. What is a transformer is actually a static device. Static, which means that it doesn't consist of the moving parts like the machine, the generators and the motors here, and is totally enclosed within the substation. So generally in terms of design, is having a tank here, and it consists of the transformer core with the winding being immersed within this tank here that has been filled with the transformer oil. So it has an oil immersed types of transformers right now. Whereas therefore with this structure, right, the chance of having fault is quite rare in the power system. But we should not neglect to have the protection scheme being implemented for the transformer. Why? Because the consequences of having the transformer fault might be very serious. For example, causing the major breakdown in the power systems, like no electricity, and it can also incur high costs for the reparations. Let's say there's a component to be on fire. All right, so now let's see what are the general faults that can be suffered for the transformer. So for example, we have 1, 2, 3, 4, 5. So the first one here, we have what we call as the interturn fault. So interturn fault is an overcurrent situation for a transformer. For example, we have short circuit occurs within the transverse winding due to the breakdown of its insulation. That is what we call as the interturn fault. The next one here, we have the core fault, or we call it as a transfer core fault. This transfer core failure indicate that the core might be overheating right now and become damaged due to high current flowing through the transverse windings. All right, it has turned into the saturation mode. And then the next one here, we have the tank failure. So if you can see, right, the structures of the transformer, it consists of a main tank here. This tank might be damaged. So this is a structural failures that could lead to the leakage of transformer oils right now, or probably the moisture outside from the environment can enter into the oil tank here, causing the short circuit conditions. So that is what we know as the tank failures. And next one, we have high voltage and low voltage pushing flashover, which is occur externally outside the transformer. So for example, this is the pushing of the transformer. We might have the lightning strike causing the damage to this pushing here. So that's how we have these situations. So for information, let's say this is a distribution transformer. The primary side will be high voltage side. The secondary side will be low voltage side. And this lightning strike or the flashover can be occurs either at primary side or secondary side of these distributed transformers. And then the last one here, we have the another kind of fault, which is high voltage, low voltage winding earth fault. So which means that we could have the winding short circuit to ground. All right. Now we have a leakage current to the ground. So that is all the possible kinds of faults you can see for a power transformer. Okay. So now let's move on here to see we have a pie chart where it's actually showing the distributions of the common transformers failures. So you can see, right, among the common failures, winding failures takes about 50%, all right, of the entire chart at 51% due to different occurrence. For example, we could have turn-to-turn fault, which is the interturns winding failure. So we have a short circuit within the same phase winding. And then we have external issue like the lightning strike causing the damage to the insulation. That's why we have the winding failures. The moistures within the oil tank that causing the short circuit within the phase winding. And then we have an external fault. And the next one here, we could have the thermal stress within the transfer winding as well, causing overheating conditions. And probably we have open circuit winding as well for the transformer. And the last one here, you can see deterioration, which means that the transformer has been aged. The winding insulation's quality might become poorer, causing the fighting failures. So this is what we have, stand high at 51%, where we can see the winding failures. The next one here, you could also find the mechanical failures for the transformer as well, which is on the tap chargers. So it stands at 19%. So what is actually tap charger here? So this is actually components we have in the transformer where we use to regulate the voltage value, either step up or step down, by changing the numbers of winding turns and hence the turns ratio. So you are changing the positions where you want to tap on the transformer's winding. This component can damage as well. So at 19%. The next one we have is 9% for the pushing failures. So the insulating structure might be aged, cracked, or something. And moving on here, we have loose connections phenomena at 6%. And hence, next one we have is a core insulations failure at 2%. So whenever we talk about the transformer core insulation failures, it can be because the core has turned into saturation mode with high voltage being induced. That's why we have the core insulation failure. And the remaining 13% here is belongs to another kinds of problems, like we have oil leakage, contaminations of the transformer oil, and etc. etc. So this is basically the distributions for the transformer failures we could have. And moving on here, let's move to the next slide. All right, so I will start to talk about different types of faults in much more failures that could result the transformer operations problems. So the first one I would like to talk about would be the interturn fault. So remember, for this kind of failures, that might be a short circuit of a fuse turns within the transverse winding, and hence it gives increase in terms of current flow through the short circuit loops. So let's check out the figures here. At the right hand side, we have a cross-section views of the transformer. So the one in gray color is actually the transformer core, all right, the magnetic materials here, and it has been wound by the three-phase winding. So we have transformers winding phase A, phase B, and phase C. So if you refer to the phase C, right, this part of the winding has been short with each other due to the breakdown of the insulation. This is what we call as the interturn fault that occurs within the phase itself. So how does this fault occur? So let's see the first point here. So This intermittent fault could be because the insulations has become damaged, breakdown due to the electromagnetic force or high mechanical force being exerted on the transistors winding. Right, let's say you have high current, you can actually causing this high electromagnetic force being generated and hence the insulations damage. And we have also another contributions factors whereby the moisture from the environment might enter into the transformer as well. All right, we know that it consists of the tank, right? This tank is filled with the oil. The moisture from the environment might be entered inside, causing the short circuit within the same phase. That is the another cause why we have intermittent faults. So for these kinds of failure, it rarely happens for low voltage transformer, but it happens for high voltage power transfer instead. Why? Because for this power transfer, right, it usually will be used together with the overhead transmissions line, which is at the outdoor. So in such a case, right, it's subjected to the problems like the lightning strike on it. So whenever we have lightning strike and hits on the transverse winding, the voltage can be very high, which could be reached to several times of the rated system voltage value. So in such a case, with such high voltage is being dragged due to the lightning strike, it can actually cause puncture, which is damage on the insulations, leading the short circuit turns within the same phase. Right? As a result, there will be very high current flowing through this short circuit loops right now, and it will whenever we have a small current flowing through from the transmissions line. So the one at the left-hand side here is actually showing the equivalent circuit for the transformer that under this problem, the intermittent fault. So you can see these parts of the transformer's winding has been shorted to each other, right? Maybe because of lightning strike, or maybe we have high force causing the damage to the insulations. All right, so now let's move on here. Now we have two photos showing the damage, right, that lead to the intermittent fault, maybe because of the lightning strike. So now you can see that this is actually the transformer winding wire. All right, so the winding wire is actually wrapped with the orange thing here, what we call it as the insulations. So as you can see, which is pointed by this operator, these parts of the winding has been short with each other due to the damage of the insulations. Okay, and the one at the right hand side, we have much more serious case, right, whereby you can tell the areas of the winding that is short with each other is actually much more bigger. So this is the samples of what we have as the intermittent fault. Okay, so now let's move on here. Now we will start to talk about core fault instead. All right. So how does the core fault occurs? So it happens because we have a high or huge fault current being flowed through the internal windings of the transformer. So as a result, this high current can cause the core lamination to move shaft and possible breach, which is inducing the AD current flowing through the transformer's windings. So every time we see AD current, which means that it will generate high heat. So we have a serious overheating condition for the transformer. Now let's check out this image here with animations. This is the transformer core with the three-phase winding A, B, and C. So if you have high current flowing through the transformer's winding, right? So current flowing through the wire, it will actually generate the copper loss, remember? So with high current, so the heat generate will be very high. So with such a case, it will cause this transformer core to be overheat as well. So if let's say we ignore this, it will actually cause to have a permanent damage, which is unable to be repaired for the transformer. So this is a sample if we have the core fault failures for the transformer. But for this core loss, right, there is actually no way for us to detect by using any electrical protection system. The reasons why is because whenever we have core fault occurs, it doesn't produce any notable change in terms of line current value, which means that the current value will not change. So you are unable to detect this by using the electrical protection system. Okay, and in addition to this, the another kinds of faults, right? I mean that causing the core fault is because we have power frequency over voltage situations. So what happens if we have high voltage over voltage situations for the power system? Yes, we know that it will actually causing stress to the insulation, causing the insulation failure. But at the same time, whenever we have high voltage induced at the secondary side of the transformer, it will also result the excessive increment in terms of magnetizing current. So we doesn't like magnetizing current for any transformer, including the instrumental transformer that we have learned, right? Once the magnetizing current increase, which means that the error operation for the transformer is actually expected, which is not desirable. All right, so what we can do if we have a core fault failures. So luckily, due to the design of the transformer, core fault still able to be detected, all right, because of this. So we know that the transformer, right, the transformer core has been submerged inside the tank that's being filled with oil, all right? So whenever we have high current causing overheating situations, what happens is with this high temperature generated, it will actually cause the oil temperature to be increased as well. As a result, it will be decomposed into gas. So for this situation, seeing as there is a gas generations, so this gas can actually accumulate and rise to the conservation stand, and we can use the Buchholz relay to detect this issue. So later we'll learn about Buchholz relay in much more details, how actually it can detect if we have overheating operations for the transformer. Okay, so now let's move on here to the next fault that result the transformer's failures. We have the tank fault, or it should be known as the oil leakage fault. So check out these figures here. These types of failure, it could be happens due to we have a crack or damage to the oil tank, so resulting the loss of oil through the leakage right within the tank. So this is a very dangerous fault, as we know oil has been used as insulations between different phase winding. And at the same time, it can be used as the cooling agent as well for the transformer operations. So whenever there's a loss of oil, this also indicate that there is a reductions in terms of insulations, and possibly we could have overheating operations as well for the transformer that operate under normal load conditions due to the loss of effective cooling. All right. Beside the oil within the tank, right, it might be contaminated. So we could have oil sludge, which is similar like the mud. So we could have the oil content, but then it can actually block the cooling accessory like the fans or the cooling ducts, as well as the pipes that used to lower down the temperatures of the transformer operations. So whenever we have such kinds of failure, let's say we have the cooling pumps as well as the fan is no longer working, which further contribute to overheating occurrence. So usually you will see that for the larger size of the transformer, it will be being equipped with such kinds of cooling accessory. But for small tanks of the transformer, we doesn't need this. Okay, so now let's move on here. So here in summary, we can say the common transformer failures we could have for the transformer occur on the winding. It could be open circuit conditions, or maybe we have overheating conditions, and the last one, of course, is the short circuit conditions. All right, so what happens if we have abnormally like the open circuit for one of the phase for the transformer, which means that we have a loss of transformer phase right now. So during the time, if the winding has been become open circuit, what is happening is we could have the undesired heating operations for the transformer. But in practice, right, relay protection is not necessarily being given to deals with these open circuit conditions. Why? Because its consequences of having this winding that has been open circuit is not so harmless as comparing to another kinds of fault. So not really need to apply the relay protection system to this. So in the event if we have such kinds of problems, one of the phase become opens, this problematic transfer can be directly disconnect from the system manually for the reparations purpose. All right, so how about the another one? So for the occurrence of abnormal overheating operations for the transformer. So what is the cause that we have overheating conditions? Usually is because we have sustained of overload condition, which means that it has been overload this transformer for long durations of time, or sometimes you might have the short circuit within the transverse winding. And occasionally is due to the failures of the cooling system. Remember the fan and the cooling motor pumps here, it might be have a problem. That's why we have overheating conditions. So again, which is similarly as the open circuit condition for a transverse winding, the relay protection is not necessarily being provided against these kinds of situations. Instead, usually we'll use thermal accessory, all right? So which means that in the event if we have overheating operations for a transformer, this high heat speed is being sent by this thermal accessory, right, will actually sound or trigger the alarm to alert the operator. And at the same time, it can use to control a bank of fans so that we can solve these overheating conditions. So you might wonder, what is this bank of fans and where does this located? So let's check out the figures at the bottoms here. So again, this is a three-phase transformer, the transformer core with the three-phase winding, let's say A, B, C phase. So this orange color thingies here is what we call it as a pushing. So we could have the incoming and outgoing pushing, or I could say the primary side and the secondary side of the transformer for each phase. Okay, you can see right for this transformer core that's being wound by the three-phase winding is actually submerged inside this tank that fills with oil. All right. And here is where the pump's located. So it's being used to stir the wire to carry the heat oil away from the transverse winding to a cooler space. And this is where we have as a banks of cooling fan, where its purpose is used to generate a cooler oil and supply to the transverse winding. All right, this is where it's located. All right, so now how about for the next one, the common failures we could find for the transverse winding, which is short circuit conditions. We have winding short circuit. This is also known as the internal faults for the transformer. So if you refer to the diagram at the right hand side here, there are three possibles of winding short circuit conditions you can see for the transformer. The first one will be like this. Let's say transformer core A, B, C phase. The first one you can see the short circuit between the same phase, like this case here. This is what we call as an intermittent fault. Remember what we have learned just now. And the next one, we could have the face-to-face winding fault, which means that we have one of the face winding is actually touching with the another face. Like in this case here, face B is touched with face C. This is what we call as face-to-face winding fault. And the third possibility, we have the transfer winding connect to the ground, which is a very dangerous types of faults. As you can see here, we have leakage current flow to the ground due to the short circuit path at phase C to the ground. So either of this winding short circuit condition, it can create a great damage to the transverse windings. All right, so now we want to see how does this winding short circuit occur. So it's usually arise due to the problems on the winding insulation. It might be deteriorate. And these deteriorations of the winding insulation can be because we have overheating operations or due to the mechanical injury as such a high force causing the damage to the insulations. That's why we have a winding being shorted to each other. So whenever we have such kinds of problems occurs, internal faults here, which is we have short circuit winding for the transformer, this problematic transformer must be disconnected in a lightning speed from the power system. Why? Because whenever we have short circuit, right, it can actually generate the arc. And this arc is with high energy, all right? See as this transformer is submerged inside a tank that's being filled with transformer oil. This transformer oil is actually flammable with high temperatures. So whenever we have arc, which means that it can cause the transformer to be on fire. So as a result, whenever we have such kinds of problems, which is short circuit for the transverse winding, relay protection is absolutely needed, all right, dealing with these kinds of failures. All right. So I have one videos here without the sound, right, where there's a guy trying to simulate the intermittent fault for the transverse winding that's being operated with 1000 ampere. All right. So I will put on this videos here. So he's actually trying to construct a transit using a toroidal core. Here is a kind of material for the core. So judging by the size of this wire here, the thicker one, we are expecting it will have high current flow. The thinner one will be for lower current. So what he's trying to do right now, he's trying to energize this transformer by supplying the voltage source at 240 watts. So it will actually connect it to the wall plug. Okay, let's see how it's do the connection. So here is where we will connect with the voltage source. So it will connect with the connectors and plug in with the adapters here. Okay. So he will try to do the short circuit within the winding here after he power up this transformer. So you can see there's a spark right whenever he short circuit for this winding. So what he's going to do next is trying to measure what is the voltage generates whenever we have short circuit conditions. In this case, with this voltage value at 1.6 something, which is quite low. So you will see that the current generated is actually very, very large. In a way, it can actually melt this aluminum foil. So let's see what happens if we connect this aluminum foil with these sections of the winding here, which is simulating a short circuit condition as well. So you can tell the high current, the temperature there is high enough to cause the fire for this aluminum foil, right? So imagine this is happens within the transfer tank. The oil is already on fire. So it's trying to measure the currents right now using the meters. You can tell right the maximum is 1000 ampere here. So whenever we have short circuit, the current is actually reaching the maximum value. Right now, he trying to do the short circuit conditions by connecting the coil in between. You can also see that the fault currents, the magnitudes, the temperature generated is reaching the melting point of this coil as well. So you can see the coil is slowly turned into red, and you will find that it's actually being deformed due to the high fault currents value. I mean, which is with 1000 ampere. So you can see the coil also being deformed as well. And next is try with this aluminum cans. So what he's trying to do is just trying to burn different material with this short circuit conditions, telling you that the current jar is super duper high until reaching a very high temperatures value. So never ever try this yourself at anywhere. All right, so I think I can stop here and move to the next topics. All right, so this time we'll look into the transverse winding connections. All right, so seeing as we are talking about the three-phase winding, right? So there are actually different ways for us, only two ways I should say, to connect the three-phase winding. It could be either in Y connections or delta connections. So what happens if you open up the transistor and look inside? The first thing you see will be the magnetic core. And each legs of the core here indicating each phase. So we have each leg here indicating each phase, all right? Each phase will be being wound by both primary winding and secondary winding. Right, so for this three-phase winding, it can be connected in either star or delta connections, right? And each phase is being displaced by 120 degrees with respect to each other. So whenever we're talking about the three-phase system, so treating as we have a balanced network, so always the signal will be different in terms of phase angle by 120 degree. All right. So now if you look into these figures here at the left hand side, this is actually showing the physical connections of the three-phase winding for the transformer with the primary side connect in delta connections. While for the secondary side, you can see, right, it's actually connect in Y connection, seeing as each phase winding has been connected to a common neutral point that has been grounded. So here is delta connections, here is in Y connections. And on the right hand side here, this is the figure showing the vectors representations for both delta and Y connections. So there is a way for us how to differentiate whether this is primary side or secondary side. So for those phase that's being labeled with capitals letters like A, B, C here, right? We actually know that this is actually referring the primary side or the primary winding. This is A phase, B phase, C phase. Whereby for secondary winding, it will be usually labeled with small letters. As you can see here, small letter A, B, and C, and now they are in Y connections. Okay, so now whenever we're talking about the transformer, its operations will always follow the magnetization curve, which is same as the instrumental transformer that you have learned in chapter 3. So what happens if we have a transformer is being energized, which means that it's supplied with voltage source. So its operations will follow the classic magnetization curve. So check out the figures at the left hand side here where we have a graph. The y-axis is now showing the flux generated at the core, and the x-axis is actually representing the current under no load conditions. So whenever we want to have high efficiency operations of the transformer, we will actually design this transformer here to be operate near to the knee point of the magnetization curve. All right. Why? This is because any increments for the voltage value, which is higher than the rated terminal voltage, or I should say higher than the knee point voltage, it will cause the transformer core turn into saturation mode. All right. So whenever we have core being saturated, so it will result excessive of magnetizing current flowing through right now. So which means that whenever we have the transformer operate higher than the nominal voltage rate, or I should say the knee point voltage here, you will notice that the flux current is actually much more higher, can be reached up to 2 times if we compare to the normal operating conditions. So high flux will cause the core turn into saturation mode. Why? Because it's unable to store this amount of flux anymore. All right, so now it will causing the improper operations for the transformer, and hence it will reduce the transformer lifetime. All right, so now this time we will start to talk about the non-true fault condition for the transformer, which is the inrush current. We have seen this since chapter 1, right? But how does this inrush current generate for a transformer? Let's see its cause of this phenomenon. So what happens if we turn off the transformer? Turn off, which means that no voltage is being supplied through the transformer's windings, right? Whenever there's no current flowing through the transformer's winding, theoretically, it should be no magnetic flux, right? Because only have current flowing through the wire, then only have magnetic fields generated. But whenever you turn it off, no current flow, it should be no magnetic fields being generated. But in the practicals, which means that in real life, there will be residual flux stay within the transformer core whenever the transformer is being turned off. So let's say this is a transformer core with three-phase winding. If there is no voltage source supply, the winding here, there's no current flow, so there will be no magnetic fields being generated. But in real life, there is a residual flux stay within the transformer core. Okay, so what happens if we want to turn on the transformer again? And due to this residual flux, right, the generated flux, which is the main flux here, should be higher so that it can compensate the residual flux. So in turn, it will cause the current being higher as well. High flux rate high current there, and this current here we call it as the inrush current. So you can see because of this residual flux within the transformer core, whenever we turn on the transformer again, it will cause the flux generated to be higher, and hence we have the inrush current. Okay, so to further understand this much more in details, we will analyze the flux and currents waveform. So the upper graph here, we have the flux being directed with respect with time that's being stored within the transformer core. And the lower graph here will be the current flowing through the winding with respect with time. Okay, so what happens if we have flux initially, all right, there in this case here, and then we turn off the transformer at this moment of time. Okay, so you can see, right, the flux generated will be being cut, and but now I have been represented with the dotted line here. Let's say it doesn't being turned off. Okay, and at the same time, at the bottom here, this is the current flow initially. If we turn it off, there will be no electric currents being flowing through the transformer, what I'm saying as no water supply to the transformer. But as being mentioned, right, there will be a residual flux stay within the transformer core. Okay, what happens if I choose to turn on the transformer again at these moments of time? So the residual flux within the core, it will actually measure from the time the transformer being turned off to the time the transformer is being turned on. So because of this residual flux, it will actually cause the newly generated flux right now become much more higher as comparing to the usual flux value. Right? And then because of this higher flux being generated in order to compensate the difference, so it will actually causing much higher current. That's the inrush current. So you can see every time we turn on the transformer again, due to the residual flux, we will have high inrush current values being observed flowing through this transformer winding. So for this magnitudes of the inrush currents value, right, is not fixed at certain value. It's actually changed based on multiple factors. So let's move to the next slide here. There are two factors that could actually govern the magnitudes of the inrush currents. So first, which is what is the values of the residual flux within the core, as well as when is the time you turn on the transformers again. So let's see these figures here to see how does the inrush currents magnitude change based on different times you turn on the transformer. So what happens? I measure the flux with respective time. Initially, the transformer is on, and this is the flux value generated. And then I have choose to turn off at these moments of time. So what if I turn back on this transformer at this time? And the residual flux right now is 0. Okay, so this means that there's no difference for the flux in the core. So I can say the inrush current value could be almost close to 0 because of no residual flux right now within the core. But what if I change the turning on point to this point instead? Whenever the main flux is reaching its maximum possible peak values here. So in this case, which means that I have the highest flux right now, so the generated flux will be very large. So in this case, I'm expecting to have large inrush currents magnitude. So what if I change to turn on the transformer at this moment instead, whereby the flux is only reaching half of the peak flux? So during this time, I have intermediate, I should say intermediate half of the residual flux within the core. So you are expecting intermediate inrush currents magnitudes. So you can see, right, based on when is the time you turn on the transformer again and what is the values of the residual flux, the inrush current magnitude is not the same. All right, and this current value can reach as high as 6 times as comparing to the nominal current value, but it will not stay for long durations of time. Okay, it will slowly go back to its rated current value. So with such a case, it is very important to know that inrush current is a natural effect of the transfer during the time we turn on back the transformer. Whenever we want to develop the protection system, whereby this protection system should not trip, else it will give us the false tripping due to this high inrush current value. Okay, so now let's move on here. Now we want to compare different parameters for the transformer during this situation. Turn on and turn off the transformer. So if you refer to these two figures, this figure at the top first during steady state condition, if you turn on the transformer, so this is the water supply, and this is the generated flux within the core, and this is the magnetizing current flow through the winding. So now under normal steady state condition, which means that you have turned on the transformer for long durations of times, you can see that the magnetizing current, which is this waveform here, its value is actually quite low, which is less than 1% of the full load current that is needed to produce the necessary flux for the transformer operations. Okay, so what if I turn off this transformer and turn it on again? So whenever the transformer is being energized at zero voltage value, so if you refer down here, this is the voltage supply, this is inrush current, and this is basically the flux generated. So if you turn on the transformer again and you notice that during voltage reach to zero value, the flux generate right will be actually very high, which is reaching 2 times higher as comparing to the normal maximum flux value. So let's say normal flux value is here. This is 2 times of maximum flux. So you'll notice that the flux is actually reaching this line right now, right? Whenever the current reaching to zero value. Okay, so what happens of these situations here with high flux being generated? It will also cause the excessive high current, high magnetizing current flowing through the transverse winding as well. This is what we call as a magnetizing inrush currents value. Of course, this high current value, we doesn't want it. We can actually lower down its magnitudes here by using the inrush currents limiters. Okay, so I think I will give you 5 minutes break first. Then I will continue the topics we have. So far, do you have any questions related to the inrush currents and the faults for the transformer? No, then I give you 5 minutes break first. Then I will proceed this topic. So please come back at 3:50 lah. Okay, so 5 minutes has passed. So let's proceed the topics we have. So just now we have stopped here where we have learned how does the transfer works, follow in which we know that it will follow the magnetization curve. And it's best for us to keep its voltage to be operates near the knee point voltage value so that we can achieve high efficiency in terms of operations. And then we also have talked about the non-true fault situation for a transformer, which is inrush currents, whereby we need to take note on this whenever we are choosing the protection scheme for the transformer. Why? Because the high inrush currents here is considered as a natural effect for the transformer during the time you start its operations, whereby what is the transformer trying to do is because it's want to compensate the residual flux within the transformer core. And what else here? We also have talked about different kinds of failures might be faced for the transfer. Like we have an open circuit winding, we have overheating conditions, and one more is a winding short circuit. And winding short circuit condition for the transformer will be the most dangerous one we could correct as an internal fault. And we must implement with the protective relays against this internal fault. So now we will start to look into the available protection system for the transformer. Okay, so let's move to the next slide. So it depends upon what kinds of failures you want to prevent from happening on the transformer. We have four different types of link system to be choose from. The first one we have known as Pucox device or Pucox relay. So Pucox relay is being used to deal with all kinds of incident faults. Example, we could have the insulation failures for the transfer winding, and then we could have a core that's been operating under high heat situations, or probably we have loss of oil as well due to the tank damage. So we can actually use Pucox relay to detect such kinds of failures. The another one we know is earth faults relay, dealing with earth fault situations, overcurrents relay dealing with the high current flow because we have overloading through the transverse winding. And the last one here, we will also talk in much more details for this chapters here will be the differential scheme here, whereby differential protection scheme has been applied to pick up overcurrent situations. For example, we have a phase short circuit to each other or all conditions and even short circuit to ground as well. So in chapter 5, right, we will not talk about earth faults relay and overcurrents relay in so much details. Why? Because you already have learned this in chapters 4. So we'll only focus on Bucock's device and the differential protection scheme. Okay, so let's start with this in the next slide here. So what is actually the Bookbox relays we have? How actually is being implemented to protect against all kinds of incidents fault? So for your information, Bookbox relay is actually a gas actuated relay. So where does this install? So it will be installed for the oil immerse transformer dealing with all kinds of faults. So it will actually install at the pipe between the conservation tank and the main tank. So you might be asking where is the pipe is. So if you're looking into these photos, right, the oil immerse types of transformer, it consists of two tanks. This is what we call as a main tank. Remember, inside fills with transformer oil and submerged with the transformer core that's being wound by the three-phase winding. And this is what we call as the conservation tank. This conservation tank will connect with the main tank via this pipe here. So what is the functions of this conservation tank? It is being used to compensate the loss of oil or the shortage of oil within the main tank. So this conservation tank is quite important because there might be a reduction of oil in the main tank due to the evaporation. So this is where the glucose relay is located or installed. So if you see this diagram, this is conservation tank. This is the pipe connect the conservation tank to the main tank. Glucose relay will install here, right, at a specific angle, which is very crucial. Why? Because this glucose relay is a very sensitive device. So how it works? So basically, glucose relay will operate alarm whenever it's gather or detect a specified amount of gas within it. Okay, so now let's move on here. So probably it will actually control by using two switch for the operations for the Brookhouse relays. Okay. So now the upper switch and the lower switch. So where is this located? So if you refer to this diagram, 3 and 3A would be the switch, the upper switch and lower switch. This upper switch will connect with the upper float, lower switch will be connect with the lower float. So based on the oil levels within this Pucox relays, right, it will actually, how to say, change the positions of the float like a buoyancy like this. All right, so what happens if I have an oil level, all right, that reduce, causing the upper float of the position reduce as well, right? So whenever the upper float position reduce, it will cause the upper switch to be turned on. So what happens if the upper switch is turned on? It will start to operate the alarm to tell you that there is a loss of oil right now for a transformer. So we could have overheating conditions. Okay, so that is the functions of the upper switch. How about the lower switch? So if let's say the oil level continue to be reduced, so we have serious situations right now. So the oil level continue reduce, and hence it will reach to the lower foot position. And this lower foot position also go down, and turn on the lower switch right now. So what happens if both upper switch and lower switch being turned on? So under this condition, this transformer will being tripped, which means that it has been disconnected from the system. We have a very serious situations right now whereby we have a serious reductions in terms of oil. Okay, so that's how does the Cox relays works. So it takes so that under normal operations, which means no fault at all for the transformer, these two switch will remain open, which means that it's turned off. Okay, so to further understand this, let's see some examples of abnormalities. How does the Cox relays works? The ideas behind is actually like this. So if you refer to these figures, this is the Bucox relay. It consists of two openings, all right? This is what we call it as the entering openings, where it will connect with conservation tank. And here we have the leaving opening here, so it will connect with the main tank. All right, so if you cut it into half, this is how it looks like. This is the cross sections views for the Bucox relay. So you can see, right, it's actually filled with oil, right? And these are the two switch located, controlled by the movable floats up and down like this. So what happens under normal conditions? So normal conditions, these two switches will remain tilted, which means that off, okay? It doesn't turn on. So what happens if we have abnormal situation? Example, we have evaporations of the oil, or maybe we have overheating conditions due to the large current flowing through the transformer's windings. So under this situation, if you have high heat being generated, it will actually cause the oil to be decomposed into gas. Remember? So for this decomposed gas, right, we actually accumulate within the Pucox relay at these areas. Okay. So with such a case with the accumulates gas here, it will actually cause this upper foot to be moved down. Okay. And hence it will turn on the upper switch. That's how the alarm signal is being triggered to alert the operator. We might have these situations. Okay, but during this instance of time, the lower floats here is actually not being affected. Okay, so because the volumes of gas being accumulated is not high enough to cause it to be go down, I should say turn on the lower switch. So the lower switch is not being activated in this case. Okay, so what happened if I have another abnormal case? I have the insulating liquid loss, which is the oil leakage problems right now. Okay, so of course, whenever we have a tank damage for the transformer, the oil actually will leak up. So the oil level will reduce, right? Reduce lesser as comparing to a normal level. So firstly, it will cause the upper flute to be go down and turn on the upper switch. So it will alert the operator. So we have an alarm being triggered. Okay. And then the oil level continue to reduce until a level where the lower fluid positions move downwards. That's how the lower switch turn on. So whenever the lower switch turn on, it will form a close connection for a tripping circuit. So as a result, the transformer will be disconnected from the power system. So that's how the Bookhouse relays works. It actually operates based on the oil levels, right, within itself to detect if there's abnormalities by using the movable fluids. Okay, so now let's see what are the pros and cons of using the Bookhouse relay. So for this, because rate is actually famous for its simplicity, right? The most simplest form for transformer protections, and it actually serves as a very reliable of indicators for something that's going wrong within the transformer, like the incidence for at the stage, which is much more easier as comparing to another form of protection scheme that you can apply for the transformer. Remember, just based on the oil level, so its operation is quite simple, but it has some downside. So for this Bookhouse relay, right, it only can be used if I have the oil immerse transfer that's been equipped with conservation tank. Remember where it's being installed? At the part between the conservation tank and the main tank. If let's say you're having a small size of transformer, doesn't come with conservation tank, basically you're unable to apply Bookhouse relays. Right? And moving on here, the other problems faced by Bookhouse relay is only able to detect the fault below its oil levels. All right, remember it operates based on the oil level. There might be something unable to be detected based on the different levels of the oil. And any unintentional vibrations or the shock might cause maloperations of the relays. So which means that if you have vibration to it, so it will actually unable to how to say detect the fault in much more accurate. So you can see it's a very sensitive relay. You have to ensure that the position is remain at these angles 9.5 degrees. So if you vibrate it, the oil level within itself is actually how to say is being affected. So it might be accidentally turned on the upper switch or probably to lower switch as well if you have vibration to this Bookhouse relays. And what else for the disadvantages for the Focus Ray? The last one here is response time is actually quite slow. All right. So typically the recorded operations time for the Focus Ray to trip the fault is at zero point 0.1 seconds. Okay, which means that the fault situation will stay there for these durations. Okay, so now let's move on to the other topics, all right, whereby we can actually protect the transformer against fault situations by using the neutral earthing. Actually, we have learned about this for the last course, okay? So what is actually the neutral earthing for a system? So basically, it's a process of transferring the immediate discharge of electricity directly to the ground with the help of the ground wire. So with such a case during the event, if I have one of the phase short to the ground, so we can actually prevent the component from damage. So for most transmissions and distribution system, the neutral point will be grounded so that we have zero reference point, let's say for the transformer. So this neutral point is actually a path where whenever we have fault situations, this will form a path for the fault current flow back to the transformer. So it's very important that the neutral point of the system is being grounded. Otherwise, it will float all over with respect to true ground. So in these situations, it will actually give stress to the insulations above its design limit. So let's check out these figures here. Let's say we have the distribution transformer. So we have high voltage, low voltage side. Let's say high voltage has been configured in Y connections. We can actually connect the neutral point with the ground. Okay. So for delta configuration, it doesn't come with neutral point, right? Later you see how actually we can implement the neutral earth for the low voltage side. So let's move to talk about high voltage side first, which is the primary side for the distributed transformer. So usually the high voltage side will be connect with the line that might be operate at 6 kilowatts or even higher. So how actually we can perform the neutral earth for high voltage side of transformer? So it's usually connect the primary neutral point by using a low resistance wire or by the means of the solid couplers. So whenever we have did this, the neutral point connect to the ground, we create as the effectively ground system. In the event if this grounding wire here is with zero impedance value. Okay, so let's check out these figures here. So for example, I have three-phase transformer, R phase, or I should say red phase, yellow phase, and blue phase. Now they are actually connect in Y connections. So for this transformer is actually feeding three-phase load, for example. So you can see right at the neutral point, it has been connect with the ground wire, which is this green colors wire here. Okay. And here at the right hand side is the vectors representation for these conditions under normal situations. If we have a balanced three-phase transformer, the voltage generated for each phase is like this, which is same as comparing to each other, same magnitude at rated voltage, displaced by 120 degree. Same applies for current as well, so it's carry the rated current flow, IR, IY, IB here, displaced by 120 degree. This is the normal current, normal voltage value. Okay, so what happens if I have one of the phase short circuit to ground? So with this configuration, so for example, for the B phase, I have short circuit path here to the ground. All right. So whenever we have these situations and I have performed neutral point being grounded, right? You will see that the fault current, which is the earth fault current, is actually flow like this. So from flow from the B phase to the short circuit path instead of flow to the load. So it's flow to the short circuit path and go back to the transformer sphere via this neutral wire. So this is how the fault current flow. So you see that with these situations, right, it gives me these advantages whereby if I have one of the phase short circuit to ground, we will notice that for the healthy phase like R phase and Y phase here, the voltage value remain the same, doesn't change at the phase voltage value higher than 0 obviously. So let's say this is a normal conditions, we are Vy, we will notice that the voltage magnitude doesn't change. Which one is changed is the B phase here, the blue phase here. Due to its short circuit to ground, it will actually try to match with the ground voltage. Okay, so you can see VB value has been dropped. How about for current value? For the healthy phase, you can see that it will still able to flow through and feed to the loads. So the current value doesn't change, same as the healthy situations. So how about for the B phase here, due to short circuit path, instead of feed to the load, it flow through the short circuit path. So you will notice that the current value will actually increase, all right, higher than the normal situations. So this is basically the advantages of the neutral earthing in the event if I have one of the phase short circuit to ground. The healthy phase here, the voltage will not change, become higher, all right? It will not rise to line voltage. It will keep at the same voltage value, okay? What is happening is just the problematic phase, drop of voltage with high current flow, okay? So what happens, for, let's say that I doesn't perform the neutral earth here. So now one situation is if I have short circuit to ground, the healthy phase, the voltage will increase higher to line voltage. That's the first thing. Okay, it might cause the insulation's breakdown. And then another situations here, we might unable to detect if I have short circuit to ground. Why? Because I doesn't have this path. So for this path, right, I can actually implement overcurrent relays here to detect if I have fault current flowing through this path right now. Okay, in the event if there's a current flowing through this neutral path, I directly can tell for this three-phase transformer that is short circuit to ground situations. Okay, and one more here is, do you still remember what we have learned for a previous course? due to the capacitive couplings of the wire, right, between the conductors, in the event if I have short circuit to ground, the capacitive current might actually cause the arcing ground present, right? This is basically the problem if let's say we doesn't have the grounded to the neutral point here. Okay, moving on here, if we are doing the neutral earthings for the low voltage side for the transformer by having the neutral point connect to the ground, as you can tell, right, the highest voltage value is just the phase voltage. Remember? So with such a case, it's allowed us to save costs in terms of insulation. So we could have the transverse winding, the insulation's grade according to their phase voltage, right? We doesn't need to withstand much higher voltage, like the line to line voltage is 415 watts. The highest is, let's say, at 250 watts, something like this. So I can save money for the insulations. And at the same time, the primary plants or the components also can be graded according to phase voltage as well. And in the event if, let's say, the surge arrestor is needed to be implemented, I can also use much more lower rating for the surge arrestors, which is like rated at 80% of the line to line voltage. So you can see, because I have just connect additional wire from a neutral point to the ground, I can save money for the components in terms of insulations as well as for a protective device here like the arresters. The only problem faced is for these situations whenever we have earth fault conditions. What is happening? The problematic phase expected to have high fault currents value. This high currents value is magnitude is super duper high, which could be approximately through the three-phase fault current, which is the highest fault current you can file for the power system. So what happens if you have very high currents value? It will give stress for the high voltage winding both electromagnetically as well as thermally. Remember, whenever we have current enter in the wire, what happens if we generate the copper loss? Where the copper loss here gives us the temperature, high heat. This heat of the fault is actually directly proportional to current square. Why? Because I square R. Okay, so whenever we have high currents, it's almost square. So the heat generated is quite high until a way that could damage this problematic phase. Okay, so now let's see how about for the low voltage side, which is the secondary side of the distributed transformer. All right, so now to perform the neutral earthing for the low voltage side of the distributed transformer, there's two ways for us to do this. All right, so depending on the configurations of the transformer winding, in the event if it's in Y connections, it will be very simple. At the neutral point, you will be connect with the earth resistor or connect with impedance value. Okay, this is the one way. The other way, in the event if it's being configured in data connection, seeing as there's no neutral point, we can actually implement this, what is known as NEC, neutral earth controller, where this neutral earth controller can control the earth resistance value at the low voltage winding side. So by having this, the neutral earth controller, whenever we have fault situations, the fault currents will can be, designed or changed to a much more manageable levels, which can be safely handled, usually in the multiple orders of transformer full load current at 300 ampere. Okay, means that you change the earth resistance value, you change the current value to become much more lower by increasing the resistance value, something like this. Okay, so now what happens if I have did this way? Neutral point of the low voltage side that's being graded. So in the event if I have a fault situation for one of the phase, this transformer will not get short, but it has this problem. All right, you will notice that the voltage value will rise this time for both healthy phase. For the healthy phase, rise to line voltage. So to further explain this, let's check out the figures here. So what happens? I have three phase winding like this: 1, 2, 3 phase. And for example, they are in Y connections. So I will have the neutral point here connect with the ground where the earth resistance, for example. So under normal conditions, if I measure the phase voltage relay, it will be V1, V2, and V3 like this. So what happens for the first phase here? I have insulations breakdown. So this first phase has been shot with the ground. Okay. So in these situations, right, you will notice that the earth is carrying voltage V1 because of the short circuit here. So it will transfer V1 to the ground. So what happens if I measure the phase voltage, right? So for the first phase, V1, because the ground also carrying V1, the voltage difference will be equivalent to 0. V1 minus V1 is 0. But how about for the healthy phase, the second phase and the third phase here? So if you measure the difference, so V2 minus V1 seen as ground carrying V1, so V2 minus V1 will be the voltage right now. So you can see from phase voltage is rise to line voltage, which is V21. Same applies for third phase here. If you measure the phase voltage now, seeing as ground is carrying V1, the voltage difference will be V31. This is actually the line to line voltage. And because of this, right, the healthy phase, the voltage become much more higher. This time, all the components at the power plant, I should say the primary plants here, its insulations has to be great according to line voltage. Instead, it's not the phase voltage, which means that you have to spend money for the insulations this time. Okay, so that is basically the neutral earthing at the low voltage side. Okay, so now let's move on here to the next topic on differential protection scheme. So this protection scheme is very important, whereby you will see it apply for many components, not only for the transformer. So you will notice next chapter 8, I also talk about differential protection scheme. Until the last chapter, I'm still talking about this. Right? So now let's see what is the ideas behind this differential protection scheme. So basically, it makes use of KCL, Kirchhoff current law, whereby it will compare the entering currents and leaving current from the protected zones. All right. And these currents, whether the enter leaving currents must be equivalent to each other under normal conditions. So what happens if I have faults? So which means that the enter and leaving current from these zones right now is different. So we have a differential currents right now. So if this differential current is more than 0 or exceeding a predetermined value here, which is a pickup current value, this indicates that we have faults occur for this transformer. So it will start to operate. Okay. So you will see that for differential protection scheme, it usually apply to the transformer. It also carry another names. It can also create as a current balancing scheme or the circulating current scheme. They're actually referring to the same thing. Okay, so let's see here. So how actually we can determine where will be the protected zone is actually based on the current transfer I'm placing. All right. So this is the current transformer. All right. One and second transformer measuring the entering currents and leaving currents. So the the components between these two current transformers here we know it as zones of protections. Okay, so it will try to compare the entering currents and leaving current from this protected zone. So here inside could be the transformer. So based on the measurement, it will actually send to the relay like this. Okay, the beauties of this differential protection scheme, right? It will actually doesn't affect by the external fault. So in the event if we have fault occurs outside the protection zone, basically it will not cause it to operate. Okay, to further understand this, let's see the next slide. All right, with a much more proper diagram as well as explanations. All right, so let's see how actually I want to implement differential protection scheme for this specific transformer. All right, so this is a transformer, primary winding, and the secondary winding. So whenever I want to implement differential protection scheme, I need to measure the entering currents and leaving currents. So I will place two current transformer outside, both side of the transformer. So one at the primary side, another one at the secondary side. And then the secondary side of the current transformer, right, will actually connect with the differentials relay. So this is the differential relay. With this coil here indicate this is the operating coil lah. Okay, so how I connect the current transfer with the relay cell obvious is with the wire. We can call it as a pilot's wire. Okay, whereby the first current transfer is measuring I1. All right, the entering current showing in these directions. So the step down current will feed to the differentials relay in these directions, whereby the second current transfer is measuring I2, right? The leaving currents here, and the step down currents will be fit into the differentials rate in this direction. So you might wonder why they are in these directions, because these two current transfer is secondary side is connect in series connection. So you'll notice that the secondary current, which is stepped down by the current transformer here, will be flowing in the same directions. Okay, because of this. All right, so now what happens if I have healthy transformer, which means no fault at all right now for the transformer? So the entering current I1 measure and the leaving current I2 will be equivalent to each other's. So this means that there is no differential current. So you can see I1 is flowing up, I2 is flowing down with same magnitude, which means that it's cancelled out. So there is no current flowing through the relay operating coil. So which means that it's not being magnetized. So under these situations, these differential recognize no faults right now for the transfer. So it will not work. So it will not trip this transformer. This is healthy case. So what happens? I have 40 transformers right now. So we might have the winding at the secondary side short circuit to ground like this case here. Okay. Under these situations, because of this short circuit path with low resistance, the current will not flow up. Instead, it will change its directions. All right, it will change its direction and flow through this short circuit path to the ground. So you will notice that the I1, I2 current now that flow in opposite direction into the transformer. Okay, so during this time, if I measure the I1 and I2 value, they are not the same anymore. So they are actually flowing at the same direction to the relay operating coil. Okay, so seeing as the current is different, which means that I have current flow here more than zero, obviously, and this current we call it as the fault current. So whenever we have current flowing through the relay operating coil, what happens is become magnetized. So with such a case, the relay will start to take action to trip this transformer. So that's how does a differential protection scheme work during the time if we have overcurrent situations. Okay. So now from previous two case, healthy and abnormal case of transfer, you see how it works. So basically, differential relay works based on the differentials current flowing through its operating coil. So how actually I obtain the differentials current here is by measuring the entering currents and leaving current and see if that is different. Okay. So in the event if the differentials currents right now is more than zero, which is reaching the relay pickup currents value, so it will start to operate. So that's how it's named at differential protection schema. Is actually work based on the difference current, right? Differentials current. Okay. So now let's move on here. There is one advantages of the differential protection scheme. Remember just now I mentioned its operations does not affect by external fault conditions, which means that these relays will not work to break the circuit in the event if I have fault outside the transformer. So let's see these examples again. So what happens? I have external fault occurs outside the transformer at the primary side. So under this situation, I have external fault. This external fault will cause both entering currents and leaving current from this transformer here to become much more larger, correct? But they are flowing at the same directions, okay? But due to this, is carry the fault currents value, all right? So the entering currents and leaving currents, which is carrying the fault currents value, is flowing oppositely to the relay operating coil, which means that if you check out the difference, it will actually equivalent to zero, right? So under these situations, you will see, right, this differential protection scheme can work perfectly as unit protections. Why? Because it's only work for the fault that occur inside these units, but not the fault outside. So under these situations, external fault, the relay will not trip. Okay, but there are some problems. All right, let's see what is the problem faced if we are using differential protection scheme for the transfer that might be causing it unable to work correctly. Okay, which means that even though there's no fault within the transformer, the relay might work, causing the false tripping. The reasons why is because the resultant differential current here might be more than zero. So let's see the first problems here. The first problem arises is actually coming from the two current transfer that's being used together with the differentials relay. So for these two current transformers, there might be a mismatch. It's not the same in terms of its characteristics due to the manufacturer defects or it already have the difference during the manufacture times. At the same time, if let's say we have unequal DC component in the short circuit current, it might also cause more error in terms of current transfer ratio. So which means that if the current transfer ratios has changed, right, it might actually cause the current flowing through here in the event if I have heavy external fault situations. So high speed current, which means that is the resultant current flowing through the relay operating coil in the event if I have heavy external fault, right? Causing here the resultant current is not equivalent to zero. So as a result, these situations, because of this current transfer having the mismatch characteristic, it will actually cause it to operate under external fault condition, which is not desired. So how actually we can solve this problem is by using a restraining coil, or we call it as the bias coil. So that's how does the relays change to another versions here, not as bias differentials relays. Okay, this bias differential protection consists of variable percentage of characteristics, which is done by adding a restraining coil like this. Okay, so instead of only having the operating coil for the differentials relay, I add another bias coil here, right? So forming a bias differentials relay. So this time I will have two passing current through this bias differentials relay. The first one is flowing through the operating current. So the current flowing through here is the differentials current or the operating current, where the differentials current can be measured by having I1 minus with I2 after being stepped down by both of the current transformer. And another current here is flowing through the restraining coil. So how actually I can find the restraining currents here is by doing the average between the two measured currents. So you can see I1 plus I2 divided with 2. That's how I find the restraining current that flowing through the restraining coil. So with these two current is control its operation. So let's see how it works in this slide. Okay. So these two current control the operations of bias differentials rate in a way if the measured operating current is more than the specified percentage of the restraining current. So this indicates that we have the faulty transformer is the internal fault. So this bias differentials rate will start to trip this transformer right now. But what happens I have previous case. So in the event is the measured differentials current right now is lesser instead as compared to the specified percentage of the restraining current. Lesser, which means that I have healthy transformer. So the bias differential rate will not work. Alright. So bottoms here is showing the typical operating characteristic of the bias differential relay in which I have a graph plot with y-axis showing the differential current that's being converted into percentage. Okay, and the x-axis here is plot with bias current or the restraining current also being converted in percentage. Now let's say I have set the bias differential relay operate at 30%, right? Which means that if I measure the operating current, which is more than 130% of the restraining current, it will actually fall at these red color zones here. So this red color zone we call it as a faulty zone. So which means we have faults right now for a transformer. So if the measure current is higher than this line at these and fulfill these situations, so the bias differential relay will start to trip the transformer. So on the other side, if you refer this bias lines again, so if the measure operating current is lesser than 130% of the restraining current, so you fall to a healthy zone. So now this bias differential rate will be restrained from working because right now this is not the internal fault. It might be the external fault causing the operating current might be not equal to zero. Okay, so under these situations, the relay will not trip. Okay, so take note for this 30%, the value can be changed. How? By changing the numbers of turns of this bias coin, which means that the higher, different turns here will give you different percentage value lah. That's how we can do the adjustment instead of 30% to another value. Okay, so now the slope of the operating curve for bias differential rate is actually representing the sensitivity of this relay. So how actually I can find the slope value is y over x naught, which is operating currents divided with the restraining current. So in the event if I have high slope, right? High slope, which indicate you can see the operating current is directly proportional to the slope. High slope, which means I need to have high differential current. So you need to supply much higher current in order to make it operate. So I can say that whenever I have high slope, this indicate I have low sensitivity for this bias differentials relay. How about on the other side here? So if I adjust the slope become much lower, so in this case, again, this is directly proportional to each other. Low slope, which means that you need much lower fault currents, or I should say lower operating currents to turn on the operations of the relay. So this indicates the relay is much more sensitive in this case. So by adjusting the slope, you are actually changing the pickup percentage of this bias differentials relay. Yeah. All right, so now let's see how does the bias differentials rate solve the problem, the mismatch of the two current transformers so that we can balance up if let's say there's any spills current flowing through the operating coil in the event if we have healthy transformer but I have external fault conditions. Okay, so let's say these two current transformers have mismatch situations. We have different CTR, for example, being used for these transformers right now, and we are implements with bias differentials relay. All right, so in the event if I have external fault occurs, which is similarly as what we have explained outside the primary side of the transformer. So now the measured currents right now, for example, at the primary side, this first current trying to give me the measuring currents I want here at 1002 ampere. And then the second current transforms here, measure the current at 1000 ampere. Okay, so if we do the difference, obviously the current is 2 amp, which is more than 0. If I'm using the ordinary differentials relay, this 2 amp will cause it operate in the event I have healthy trends but with external fault. But what happens I have bias differentials relay? I need to look for restraining current as well, right? So to find the restraining current will be average of these two, 1002 plus 1000 divided by 2. So you find the current restraining current at 1001 ampere. But don't stop here. You have to see how much percentage you have been set right now. For example, if we set it at 20%, so we have to find 120% of the restraining current. So 1.2 multiplied with this. So 120% of restraining current is 1201.2 amp. Okay, so now let's compare the operating current and the restraining current. Now, the operating current, this differential current is less than this, right? So when in the event, if the differential current is less than 120% of the restraining current, the relay will not work to trip the transfer. Why? Because this time is not the internal fault, this is the external fault that causing the operating current here is not equivalent to 0. So that's how Bayer's differential relay works to solve the mismatch of these two current transformers that giving us the different measurements value. Okay, so now in the event if we are using differential relay, you have to ensure the current transfer in terms of ratio is used for these two current transfer here must be equivalent to each other in order to avoid maloperations of the differentials relay. Okay, so now let's move on to see the another problems we have. Okay, so the another problem that might also cause the differentials relay are unable to work properly is due to the saturations of the current transfer. So again, the problem comes from these two components. Okay, so whenever the full currents of the transfer at both sides is different, okay, under this situation, the current transfer ratio at both sides will difference, and hence it will also cause the saturation characteristic different as well. So what happens if I have one of the current transfer to be saturated first before the other? It will lead to the differential current flowing through the operating coil. So to further explain this point, let's check out this image here with the explanations. So this is the transformer. I'm using these two current transfer for the measurement, entering currents, leaving currents, and the measure current will feed through the differentials relay. All right, what happens under healthy condition or I have external fault situations, and this first current transfer has turned into saturation first. So this means that the first current transfer unable to give you the correct reading, so it might measure the wrong currents value because saturated. And the another one here can give you the correct reading, so it give you I2 value. So if we find the difference between these two, obviously is not equivalent to 0, right? That's how the differentials relays start to treat this transformer in the event if I have one of the current transfer become saturated. So what is the solution to this is select the right current transformer lah. Yeah. So how so is by choosing the right knee point value for the current transformer. You have to ensure that the situations doesn't causing it to be operate over than the knee point voltage, else it will give us the wrong reading due to it has been saturated. Okay, so this is the second problem, and here would be the solution. Okay, the third issue coming from the transformer itself due to the tap changing. Okay, so the power transfer usually being provided with the component which is known as tap charger or the tapping here, but it's allow us to change the AC voltage levels. And for the current transformer, the one that used to measure the entering and leaving currents here, the ratio is select based on the basis of the normal tap, which is under normal situation with this situation with the voltage value operate. So what happens if you need to change the voltage value, which means that it will change the tap position, changing the turns ratio. Under this situation, due to the change of the turns ratio, it will cause the currents that is carried at both sides of the current transfer to be not the same anymore. So this indicates that under healthy operations of the transformer, there will be spills current, which is the differentials current flowing through the differentials relay operating coil. So now you just change the voltage value from the transfer, it causes this differentials relay work under normal situations. Of course, this is not desired. This is the mal operations. So what we can do to solve the problems here, also using the bias differentials rate, strongly bias, which means that the bias percentage is much more higher, so that we can avoid such uncalled tripping, which is undesired tripping. Okay, so the fault problems here also coming from the transformer itself as well due to different connections for the three-phase winding, whereby the way we connect the primary winding and the second winding of the transformer will actually cause the primary current and the secondary line current to become out of phase. So for example, we know we have Y delta connections that if you have primary side with Y, secondary side with delta, or reversely, primary side with delta, secondary side with Y, with these combinations of different connections for the three-phase winding, it will always give you 30-degree phase shift for the measured current. Okay, so to prove this, we need to draw the phasor diagram. So let's check out this figure first. So how I know that it's always 30-degree phase shift for different connections of the three-phase winding? You can clearly see if you superimpose the Y and delta connections. Like this case, this is Y. You superimpose with the delta connections and measure what is the phase angle difference. You will notice that always has 30-degree phase shift. Okay, so now I want to plot out the phasor diagram showing that is the out of phase by 30-degree for both primary side and the secondary side. So to do so, I need to find the line current at both sides. So for example, if I have delta and Y connected transformer, okay, at the primary side and the secondary side respectively. So if I want to find what is the line current model for each phase, R, Y, B phase, I will need to apply KCL at this node, right? So the entering current, I have IRL plus one more here, I have IB equivalent to the leaving current, which is IR. I will need to rearrange in terms of line current. So IRL, so I have IR minus with IB. That's how I can get the line current at the primary side. So how about for secondary side here? So whenever I have Y connected three-phase winding, the line current and the phase current is actually the same, right? Because I have only one path for the current flow. Okay, IR, IY, IB would be the line current at the secondary side. So now let's draw up the phasor diagram to show the 30-degree phase shift for both primary current and the secondary current. So now you will see if I put this current's value in the vectors diagram, you will observe that the secondary current, which is Y connected, and the primary current, which is delta connected, they should be in phase. Why? Because both winding is mount on the same leg of the cord. What means by same leg? If you go back here, this is at the front, this is transformer comma, one leg, second leg, and the third leg here. Both primary winding and secondary winding is within the same leg of the core. All right, so they should be in phase. But right now, because of different connections, it become out of phase by 30-degree like this. So if you combine together, so this is the secondary current, this is the primary current. Now you notice that in the event, if I have delta Y connections, I will have 30-degree phase shift between the secondary current and primary current, talking about the same phase. So if whenever we have delta Y connection for the transform, I have positive 30-degree connections because right now the secondary current is leading in front the primary currents by 30-degree. But how about if I have reverse connections? I have Y delta connection instead. So you will notice that I have negative 30-degree connection instead, which means that now the secondary current is lag behind the primary current. Okay, that is what we have as negative 30-degree connections. Okay, so to further us understand this, so now we will move to the next slide here. All right, you can actually see how does the phase shift change by using the clock lah. So in the event if I have combinations of delta Y or Y delta connections as being mentioned, always there's a 30-degree phase shift between the secondary currents and the primary line currents, right? So what happens if I have delta Y connections as being explained? We are expecting to have 30-degree positive phase shift. So let's say this is the clock, right? So I have 0 degree at the tops here. So whenever I have delta Y connection, you will notice that the phase angle will show at here is 11 o'clock, right? Positive 30 degree. So this indicates that if you plot out the current waveform, The secondary currents will actually leading in front the primary currents by 30 degrees. So how about I go the another way around, Y delta connection instead. So you will see the clock will plot at 1 o'clock, negative 30 degree. So under these situations, if you see the waveform for both primary and secondary line current, now the secondary current is lag behind the primary currents by 30 degree instead. Okay, so as long as there is different connection at primary side and secondary side, delta Y or Y delta always have 30-degree phase shift. But what happens if I have same connections at both sides, delta delta or YY connections? This time I will have 0-degree phase shift instead. So in the event if I have phase shift difference between the current, it will actually causing the spills current flowing the differentials relay. So it will actually trip the healthy transformers right now. So what is the solution to solve this phase shift difference between the primary current and the secondary current? So now this is the transformer. So now the primary side is in delta connections, secondary side in Y connections. So in order to implement with differential relay, so this is the differential relay, the relay operating coil, I will need to measure the current, right? See, as this is three-phase transformer, I will need to apply three current transformer and at the output side as well, right? There are another three sets of current transformer measuring the leaving current. So how actually I can solve the phase shift difference between different connections at both sides. Right? I can actually compensate by having the proper connections of this three-phase current transformer. So in the event like this case here, the delta connected at the primary side, the current transfer that we use to measure the current, it has to be connected in Y connection, which is counter to the transformer connections. So how about for the secondary side here is in Y connections. So for Y connected secondary side, the current transfer that you use for current transformer, you will need to connect in delta connection instead, right? With these proper connections, it can actually compensate the phase angle 30-degree difference. So as a result, there will be no passing currents flowing through the relay operating coil. So that's basically is how to solve these problems here. So after the proper arrangements of the CT, the current transformer, the current flowing through each phase right now, considering both primary currents and the secondary current, will be in phase. So if you see the phasor diagram, this is from the transformer, primary side, secondary side. This is the output coming from the current transformer at the primary side and the secondary side. So if you compare in terms of current output from the current transfer, so referring to R phase or the red color phase here, this is primary side after the current transformer. This is secondary side after the current transformer. You can see they're actually in phase right now. Same apply for the blue phase here or the yellow phase. They are actually right now to be in phase after you have do the right arrangements of the three-phase current transformer. So with these situations, no spills current flowing through the relay operating coil under normal conditions. Okay, so now let's move on here. We have still much more problems for the differential protection scheme. The next one is because of the inrush current, so which is during the time you turn on the transformer after it's being turned off. So the energizations of the transformer might lead to the maloperations of differential relay due to the inrush current. So now which means that whenever we supply water source to power up this transformer under no load condition, no load, which means that secondary side doesn't connect with anything. So during the time you turn on this transformer at the primary side, you will notice that there will be high inrush current, where its value can reach up to 8 to 13 times of the full load current value. So for this inrush current is actually reached in second order harmonic, and it can actually cause the maloperations of the differential relay. Obviously, right now here no look ma current zero at the output side. The primary side is high inrush current. Obviously, the differential current is more than zero. So it will cause unnecessary tripping of the differential relay. Okay. So what we can do to solve these problems here, so the solution can be found in the next slide. So we can actually use differentials relays with the suitable sensitivity, all right, which we can use to cope with the magnetizing current, which is the inrush current. So usually we'll use it together with the time delay, which means that we will need to go through the inrush currents period, all right, so that this relay will not work. This is the first solution. Okay. The another solutions I can use harmonic restraint circuit, or I should say a supervisory unit here together with the differentials relay. Why? Because this is high in second order harmonics, correct? So now we can actually use this harmonic restraint circuits here to stop the operations of the differentials relay whenever we power up the transformer. All right. This is because it's able to tell us the difference in terms of waveform shape for both inrush current as well as short circuit condition, which is a true fault situation. The waveform is actually different. So that's how we use the restraining circuit here to stop this differential relay to work under the moment if we turn on the transformer that expecting to have high inrush current. Okay, so let's see the last problems for the differential protection scheme that might cause it maloperated, which right now for a power transformer itself, the core can be saturated. So what happens during the time if we have the saturated core? So any increase for the voltage values will increase the magnetizing current, which is very, very significantly. Remember the definition for the knee point voltage. So after you have the transformer operate higher than the knee point voltage, with small increase in voltage value at the secondary side, let's say at 10%, it can give you 30% increments in the magnetizing current. All right, that's probably the problems right now if you have saturated core for the transformer. So with such a case, it can actually increase the operating tendency of the differentials relay, which is maloperations. So what we can do to solve this problem, the remedy, which is a solution, is to use fifth order harmonics bypass feature, right? Which is actually aligned with the magnetizing current, in which is reached in fifth order harmonic. So we can bypass this, and hence the saturated core will not cause the maloperations of the relay. All right, so with such, I think we are reaching the ends of the chapters here, which is actually a small chapters. So we have talked about the protection scheme for the power transformer, talking about different kinds of failures like the internet faults, the tank failures, low voltage, high voltage pushing flashover or short circuit to ground, and the core saturated can actually cause the wrong operations of the transformer. And then we also have talked about the inrush currents, the natural behavior of the transformer in which any protection scheme you implement should not treat these situations during the time we turn on the transformer. Okay, so you have see how it occurs, why inrush current, how it's being generated due to the residual flux. Okay, and then we also have go through different protection scheme that you can apply for the transfer in much more detailed manner for both Bucox relay and differentials relay. And differentials relay you can actually modify as a bias differentials relay to solve some problems like the mismatch of the current transformers ratios and all. And then we also have talked about the 6 Plowman phase as well whenever we are using differential protection scheme for the transformer. All right, so I believe this is everything we have learned today. Do you have any question to ask me? Oh, are you sure? Okay. So for this topics itself, right, we have a tutorial for it. So please try out the tutorial questions. And if you have no question, that's it for the day. And I will see some of you on this Friday for the second lab. Please come. All right. So thanks for your attention and see you.